tower turned bright yellow and then white, essentially, and there's this enormous roar, and then you're on your way.
I guess about 5-10 seconds into the flight, I realized that I was still intact and that we were pointed in the right direction and we were going up.
When the solid rocket boosters light off, you're on your way someplace. It's 5 million pounds of thrust, and you're getting up and going right now.
At about 15 seconds after our liftoff, I was saying to myself, Ross, what in the world are you doing here? Because it was quite a thrilling ride.
In centuries past, the oceans were our major challenge. What we found beyond the horizon changed everything. Commerce, culture, indeed our very way of thinking, our consciousness of the nature of our world. After the oceans, we took to the air. This time, things went much faster. Unlike the technologies of the sea, those of flight evolved so rapidly that we went from Kitty Hawk to the moon, not in centuries, but in the span of a single human lifetime. For me, the sea came before space. As a naval commander, and then as a scientist working aboard the space shuttle, I learned firsthand what it takes to function in an alien and hazardous environment. Pushing on over the horizon takes more than imagination and willpower. It also takes technology, new and better machines, faster, more powerful means of propulsion. The technologies of the sea and those of flight can be seen then as tangible expressions of the human urge to explore. Our push into space has sprung from a natural desire to fly farther, higher, and faster. It's given us triumphs and tragedies, achievements and setbacks, all enveloped by an aura of excitement and danger. But it wasn't until I was training for my own flight aboard the shuttle that I witnessed up close just what it takes to put people into space and to keep them there. So in the next 6 programs, we'll look at all of the crucial elements that have to come together to make the space experience possible. We'll look at the vehicles that get us up there, the protection we need to live in an alien environment, the work we'll do, the wealth we'll create, and the knowledge that we seek. In the past, our drive to explore the oceans, to find new lands, and to create new wealth was transformed from dream into reality by a marriage of technologies, such as the power of sail and the instruments of navigation, timepieces, sextants, compasses, a marriage that allowed explorers to circumnavigate the globe. In the same manner, our journey into space has been made possible by the merging of new technologies, the power of rockets and the guidance of computers. In the first program, we'll look at rockets, how they're produced, how they work, how they're controlled as they open the door on our newest world. A rocket launch is little more than a controlled explosion. Harnessing these incredible forces remains one of the greatest challenges we encounter in our push into space.
Because of the almost routine success of rockets and the shuttle over the last many years, people have been lulled into a sense of routine operation or ho-hum sort of attitude. And it's frequently overlooked that we're dealing with very complex and difficulty-prone hardware. I think that when a rocket fails to operate properly or in fact blows up, which occasionally happens, it's a recognition of the fact that this is a very risky business and will continue to be so. It will never be totally routine, and it's probably good sometimes to be reminded of that.
so it's really firm in there. Because what happens, once it starts heating up, the masking state starts to give and it's going to slide out. You don't want that. Now what you do, once you've done that, turn the rocket upside down, nose cone down.
Simple rockets have been around for thousands of years. Model rocket clubs today use virtually the same technology first invented by the Chinese thousands of years ago.
Then just kind of fold it over with your finger.
Large or small, all rockets operate on the same basic physical principle of action and reaction. According to Newton's third law of motion, for every action, there is an equal and opposite reaction. In the case of a rocket, the action is the downward rush of hot gases at high speeds, and the reaction is the upward movement of the rocket off the ground.
4, 3, 2, 1.
These tiny rockets, fired by gunpowder, can generate enough thrust to get themselves off the ground, but they're no match for the pull of gravity. The cost of defeating gravity comes high. It takes a lot of energy to propel a payload all the way into Earth orbit. Different rockets do it in different ways. They may have a single engine or several. Some rockets are made up of a number of stages stacked one on top of the other and designed to fire in sequence. Others have boosters strapped to the side that burn fast and then fall away. The three-stage Saturn rocket weighed 58 times more than the tiny Apollo capsule and the three-man crew it lifted to the moon. The Redstone facility, Huntsville, Alabama.
Okay, the vents are closed.
Here, Werner von Braun started development of the rockets that ultimately carried men to the moon.
So we're ready to go.
The testing goes on today. Rocket engineers are always looking for better designs, better propellants, fuels that are more powerful, more efficient, more manageable.
Here we go.
A propellant combines both fuel, a source of energy, and oxidizer, a source of oxygen, to make the fuel burn. This is what gives a rocket the ability to function beyond the Earth's atmosphere. Propellants come in different forms. Dr. William Stevenson, head of the Redstone Research Program, describes the differences.
Basically, there are only two basic types of rockets, and that is the solids and the liquids. The solids have propellants which can be stored. The solid rocket motors are very simple. They're easy to use. They have very few moving parts. And most of the engineering goes into the design of the chemical formulation of the propellant itself. Once that's done, it's pre-programmed. Once you start the fire, you can't put it out, you can't stop it, you can't turn it off. It's going to go ahead and do its chemical reaction, generally speaking. On the other hand, the advantages of liquids are that they can be controlled better. They can be turned on and off. The energy can be managed. You can speed it up or slow it down. A disadvantage is that you can't generally store those kinds of systems. You must fuel them a short time before you're going to use them. I think the solid rocket motor is the simplest kind of rocket motor. It has a steel tank with a nozzle on it, but a very simple device, and propellant is cast in the rocket motor, and this would represent the propellant here. The propellant is a combination of fuel and oxidizer, and as this propellant burns, the gases, combustion gases, move out the nozzle, and for this reaction, hot gases are shoved aft and the container is shoved forward. And that is the basic principle of rocketry. These are some of the components that go into a solid propellant. This is a polymer. It's actually a liquid rubber, has the consistency of honey, and it's the first thing to go into the mixer. This serves two purposes. It holds the materials together. Eventually, this will turn into a solid like this rubber we have here. It's a binder that holds the solids together. Another part of the fuel is the aluminum powder. Aluminum burns to give a great deal of heat, and it's a basic component in many solid propellant recipes. The oxidizer is generally something like ammonium perchlorate, which is a white crystal, as you can see, looks kind of like sugar, or it could be ammonium nitrate, which is a fertilizer type material. And those things are added to the mixer, and Mr. Wayne Clayton is our mix technician. He's going to show you the process for this. The liquid polymer is added first. This is a small experimental mixer. It'll take about a 1 pint capacity, and it's located here in this room, which has 3 explosion-proof walls and then a blowout panel on the other side, because occasionally we do have fires in making experimental recipes. This particular mix is what we call an inert mix. We don't anticipate any problems with this. When the mix is completed, the propellant looks very much like this. It's in a doughy consistency, but it has some fluidity and it will flow. It's poured into a mold, which is a rocket motor with a former down the center of it. The whole assembly is placed into an oven and heated for several days, and at that time the center mold is removed and you are left with solid propellant cured in a solid form. Sometimes the aft end of the motor has a slightly different geometry. But as the igniter, which is in the head end of the motor, is ignited, flame is flashed down the center hole in the rocket motor, and the propellant burns from the inside out, and that's the way most rocket motors operate.
A test firing of a shuttle solid rocket booster. £2.5 million of thrust. Once fired, this rocket cannot be turned off. It will keep going until its propellant is totally burned out. But not all rockets work this way.
But the primary difference between the solid propellant rocket and the liquid is that in the liquid there are 2 tanks, and the engine is very small relatively, but one of the liquids comes out of a fuel tank and another comes out of the oxidizer tank, and the missile again looks like that. This might be something like kerosene. This might be something like liquid oxygen. And they're both fed into the engine, and they burn at this point, and the hot gases move aft, and the container moves forward. This is a much more complex system because you need valves in order to regulate the rate at which the liquids go into the engine. I need a pressurizing system which will move the fuels and the oxidizers into the combustion chamber, which is right here.
A liquid-fueled engine requires intricate plumbing, valves, pumps, pipes, and the technology needed to keep explosive propellants hundreds of degrees below zero. This is the price we pay for a major advantage in liquid engines. Their thrust can be varied and fine-tuned. 5 powerful liquid-fueled engines generating 7.5 million pounds of thrust propelled the Saturn rocket and the Apollo spacecraft off the Earth and on its way to the moon. Liquid propellant rockets are more complex than solids, but they can be more easily controlled, a major reason why they are used in the manned space program. Unlike solids, liquid-fueled engines can be shut off and restarted by controlling the flow of fuel and oxidizer into the combustion chamber. The space shuttle is a hybrid, the first manned vehicle to use a combination of solid and liquid rockets. When humans are on board, controllability of the launch pad is particularly important, a characteristic of liquid fuel rockets that was dramatically demonstrated in a shutdown of the shuttle main engines mere seconds before liftoff.
Presentation recorder's going to record. T-minus 31 seconds. We have a go for auto sequence start. Discovery's 4 redundant computers now taking over primary control of critical vehicle functions through liftoff. We have a go for main engine start. 7, 6, 5. We have main engine start. We have a cutoff. We have an abort by the onboard computers of the orbiter Discovery.
Had the solids fired, there'd be no stopping the launch. No matter what kind of rocket, once launched, not much can be done if things go wrong. And things can still go very wrong.
Rockets are dangerous because we are playing with fire. And that's exactly the reason. We are mixing fuels and oxidizers, and we are attempting to control them. That is the job of the research scientist in the rocket business, is to attempt to control that fire. Most of the time we do a very good job of that. We understand the processes and we know what we're doing. Occasionally unexpected things happen, and we learn from those and move on to a better control of the future.
Breaking the bonds of gravity is the first job, but not the only one. The atmosphere is a formidable barrier to the rocket's passage. As it plows its way through the thick, lower layers of air, the vehicle encounters resistance and buffeting. Its sleek aerodynamic shape is intended to reduce these effects to a minimum.
4, 3, 2, 1, fire.
Clearing the densest part of the atmosphere in as short a time as possible is a must. That's why launches are almost always vertical. The objective is to propel a payload into orbit around the Earth, a human being to the Moon, or a probe to Saturn. So why do we need so much power? Well, it's the speed of a rocket that determines how high it will go and whether it can propel a spacecraft into orbit around the Earth. If it's not going fast enough, then sooner or later, it'll fall back to Earth. This is how it works. Imagine this to be the Earth, and on the Earth, we have this very tall tower. And you're at the top of that tower, and you're holding a ball. If you drop that ball, it'll fall to the base of the tower. If you throw it, on the other hand, it'll describe an arc and fall at some distance from the tower. If you throw it even harder, it'll describe a larger arc. Now, suppose you were very strong and you threw it very hard. It could conceivably go all the way around the Earth and hit you in the back of the head. In that case, we would say that that ball was in orbit around the Earth. Now, the key here is to throw it fast enough. To get an object in orbit around the Earth, you have to throw it to reach a speed of 28,000 kilometers per hour. Now, let's say you were even stronger than that. If you could throw it to reach a speed of 40,000 kilometers per hour, well, in that case, the ball would go off like that, to the Moon or to the planets. And that's why you need so much power to escape Earth's gravity. The first 150 kilometers is the most difficult part of the journey into space. Once in orbit, no longer fighting Earth's gravity, the rules change. It's not that the effects of gravity disappear. They don't. In fact, the gravitational pull of the planets can be used to slingshot a spacecraft right through the solar system. The result is a long, looping game of catch-up. In space, getting where you want to go no longer takes the sheer brute thrust of mammoth engines. Much less power will do the job. And since there's no atmosphere, Vehicles that fly only in space need not have the streamlined, bullet-shaped profile needed to get off the surface of the Earth. In the next century, we may see a whole new generation of innovative space vehicles designed to operate beyond the Earth's atmosphere, to ply the spaceways between the Earth, the Moon, and the planets. They will be unique. Unlike any flying machines we know on Earth,
using a spacecraft with a long cable attached to it, not just a few hundred feet, but tens of miles, or even 100 or 200 miles, you can release objects on the end of this cable, swing them up, or even just extend them out into space, let go, and they will go off with their own momentum, off on new directions, new orbits. Now, you can do that upwards, you can do it downwards toward the Earth. You can lower the cable toward the Earth so that a spacecraft or a rocket taking off from Earth doesn't have to get into orbit by itself. It can only reach the lower end of the cable and hook on and be pulled into space. Those are some of the concepts which, in some ways, are even too imaginative for science fiction. But they look like we'll see a lot of them next century. Once we're in space, then too, we have other alternatives, nuclear thrust systems, solar sailing, using the pressure of sunlight, and vast sails to take us off out to the moon, and even beyond that, interplanetary flight, for almost no cost in fuel. These are technologies which I think we'll see in the next several decades. It's why I, for example, suggest that it's not much use in planning now for a flight to Mars in 20 years using these old techniques, because within 20 years, we'll have accessible a number of new technologies that'll make a flight to Mars not in 9 months or 10 months, as we now think, but in a month or a week. In that case, it's an entirely different kind of project.
the future may hold many new and exotic vehicles. But for now, we still depend on the power of chemical rockets to get off the Earth.
Well, that was good. That went the highest, probably.
Gravity holds us with a tenacious grip. The first 100 kilometers, indeed the first 100 meters, is in many ways the toughest part of the journey. The actual distance is trivial. The cost and effort required to cross it are not. It is this first step that demands the most powerful engines ever developed and costs millions of dollars a shot, all for a 10-minute ride into lower Earth orbit.
Your eyes are seeing this dazzling light show and flames and smoke. Your body was being virtually shaken.
Then the solids come off, and when the solids come off of the sides, they have little rockets that push them off, and those rockets spew flame over the cockpit. So when the solids come off, the cockpit is pretty much engulfed in flame. The solids are off, and you're on the main engines, and those are glass smooth. It's like riding in a big electric elevator.
What was remarkable was how quickly the blue sky turned black. Space is a lot nearer than you think. You have to go very fast to be able to stay up in space, but it really doesn't take very long to get there.
You're not in any big hurry to unstrap and start moving around, because it's a new sensation, and you want to sit there and not move anything for a few minutes. And you're very busy getting the orbiter reconfigured anyway, so there's no big hurry. But the whole launch is no doubt the most exciting part of the flight.
I don't think that you breathe easy until the main engine's cut off and you're in space. But that's very exciting because you're sort of being crushed by about 3 Gs right before the engine's cut off. And then they cut off quite nicely, and then everything floats. And to see your arms floating out in front of you and the pencils floating around, you can just feel the smiles developing on everybody's faces because you know that you've arrived, and it's a very exhilarating moment.
Shot out of the atmosphere, our space travelers now find themselves in a unique and hazardous environment, with extremes of temperature, a near total vacuum, increased levels of radiation, and of course weightlessness. It's an environment that the human body has never before encountered, nor is it inherently equipped to survive it. In the next episode, we'll examine life support, the technology that allows us to live for longer and longer periods in space. As the journey continues, the challenge now shifts to staying alive.
Discovery Houston, it looks like you're heading toward the right place.
We think so. Yeah, Dave, I believe we got a tally-ho on it.
Roger that. That sounds pretty good. Old Eagle Eye's up there.
Discovery now within 50 miles from CENTCOM and closing. And the KU band rendezvous radar is activated and is locked onto CENTCOM and is in the passive mode.
And now you're going to close on CENTCOM.
Roger that. We got a bunch of guys looking for it out the top window here.
Discovery has come around into attitude and is now about 331,000 feet from CENTCOM.
And we're cutting the corner on it now, by guys.
That you are. You might even have some radar detects by the time we get you to...
That after